This is the EdExcel AS Level Further Maths Paper 1 from the June 2025 series. Question number 1. We are given z equals root 3 subtract 3i. Part A. Write z in the form r multiplied by cos theta plus I sin theta, where theta is in between negative pi and pi. Here we have z. We can use our calculator to find out what r is and what theta is. Let's key in z. We have root 3 subtract 3i. And now, if we go to the catalogue, go to the 7th option for complex number, and the 6th option where we can find out what r and theta is. And if we execute, you will find r to equal 2 root 3 and theta to equal negative pi over 3. Hence, z is equal to 2 root 3 multiplied by cos of negative pi over 3 plus I sine of negative pi over 3. Part B. Show and label on a single Argand diagram the point P representing z and the point Q representing IZ. To begin with, let us find out what IZ is. IZ is equal to I multiplied by z, which is root 3 subtract 3i. So let's multiply I by root 3 subtract 3i. So in our calculator, we have I multiplied by root 3 subtract 3i. It turns out we end up with 3 plus root 3i, and therefore P, which is represented by z, is given by root 3 negative root 3, and Q, which is represented by IZ, is given by 3 root 3. Here are the points P and Q on a single Argand diagram. Part C. Describe the geometrical transformation that maps P onto Q. We want to go from P to Q. So, we have P, which is root 3 negative 3 as a vector, and we have Q, which is 3 root 3 as a vector. And so I need to multiply P by some matrix to get Q. Now, if we think about our first row, we could have 0 and negative 1. That's because if I multiply 0 times by root 3 and add that to negative 1 multiplied by negative 3, I get 3. And for my second row, I would have 1 and 0. And that's because if I multiply 1 by root 3 and add on to that 0 multiplied by negative 3, I end up with root 3. So we have the matrix 0, negative 1, 1, 0 multiplied by the vector P, which is given by root 3, negative 3, and that gives us the vector Q, 3, root 3. This matrix here, 0, negative 1, 1, 0, would represent a rotation 90 degrees anti-clockwise about the origin. Question number 2. f of z is given by 4z cubed subtract 12z squared subtract 95z plus 325. Given that f of negative 5 equals 0, part A, determine f of z in the form z plus a multiplied by bz squared plus cz plus d, where a, b, c and d are integers. To begin with, if we know that f of negative 5 is equal to 0, that would mean z plus 5 is a factor of f of z, meaning we would have z plus 5 multiplied by some quadratic bz squared plus cz plus d being equivalent to 4z cubed subtract 12z squared subtract 95z plus 325, and so a will be 5. For us to determine what b, c and d are, we can compare coefficients. If we take a look at the z cubed terms, on the left hand side we would have z multiplied by bz squared, so the coefficient of z cubed on the left hand side is b, and on the right hand side we have 4z cubed, so the coefficient of z cubed on the right hand side is 4, so b is 4. Let's now take a look at the z squared. We have 5 multiplied by bz squared gives us a z squared term, and then we would have z multiplied by cz, which would also give us a z squared term. So the coefficient of z squared on the left hand side would be 5b plus c, and on the right hand side we have negative 12z squared, so the coefficient of z squared on the right hand side is negative 12. We know that b is 4, so we have 5 multiplied by 4 plus c equals negative 12, meaning c is equal to negative 32. Let's now take a look at the number terms. On the left hand side we have 5 multiplied by d, and on the right hand side we have 325, meaning d is equal to 65, and so therefore f of z can be rewritten as z plus 5 multiplied by 4z squared subtract 32z plus 65, and of course this will be equivalent to 4z cubed subtract 12z squared subtract 95z plus 325. Part B. Hence show that the complex roots of f of z equals 0 are 8 plus minus I over 2. If we have f of z equaling 0, that would mean we would have z plus 5 multiplied by 4z squared subtract 32z plus 65 equaling 0. And so we would have z plus 5 equaling 0, or we would have 4z squared subtract 32z plus 65 equaling 0. If we have z plus 5 equaling 0, that would mean z would equal negative 5. Let us solve this quadratic to find out what z is. Z will equal negative 32 plus minus the square root of negative 32 squared subtract 4 multiplied by 4 multiplied by 65 all over 2 times by 4. So we have negative 32, that's 32, and then we have plus minus the square root of. Now if we evaluate the bit underneath the square root, we would have negative 32 squared subtract 4 multiplied by 4 multiplied by 65, that is negative 16, and we divide this by 2 times by 4, which is 8. So now we can find out the value of this. If I press the settings key on my calculator, then the second option for complex mode, we can give answers in the form a plus bi. So now if I input this, I have 32 plus the square root of negative 16 over 8. So we would have 4 plus a half I, and of course we would also have 4 subtract a half I, or equivalently 8 plus minus I over 2. Part C. Determine the values of z such that f of 2z subtract 1 equals 0. For part C, let us begin by letting w equaling 2z subtract 1. And so, from the second part of the question, we know that f of w equals 0 has roots w equals negative 5 and 8 plus minus I over 2. We know what w is, that's 2z subtract 1, so we would have 2z subtract 1 equals negative 5 and 8 plus minus I over 2. To find out what z is, we would have to add 1 and then divide by 2. So negative 5 plus 1, that's negative 4, and dividing that by 2, we end up with one of the solutions being negative 2, and for the other solution, well, we have 8 plus minus I over 2, or equivalently 4 plus minus a half I. If I add on to this 1 and then divide by 2, we end up with 2.5 plus a quarter I, or equivalently 5 over 2 plus minus I over 4. So we have z equals negative 2 and z equals 5 over 2 plus minus I over 4. Question number 3. We have the 2 by 2 matrix M, which is given by A, B, negative 1, negative 1. A and B are real constants and A does not equal B. Part A, we have to find the inverse of M in terms of A and B. To begin with, we need to find the determinant of M, and that's shown here. So we have A multiplied by negative 1 subtract B multiplied by negative 1. The determinant of M is given by B subtract A. So M inverse will be given by 1 over the determinant of M. So we have 1 over B subtract A multiplied by, now here we need to transpose the matrix. We need to swap the A with the negative 1, and we need to swap the negative 1 with A, and then we need to multiply the diagonal by negative 1. So we have negative B 1. Here is the inverse of M. Given that the matrix M plus the inverse of M is equal to I, where I is the 2 by 2 identity matrix, part B, determine the value of A and value of B. We have the equation here. We have the matrix M, which is A, B, negative 1, and we add on to this the inverse of M, which is 1 over b subtract a multiplied by negative 1, negative b, 1, a. And this is equal to the 2 by 2 identity matrix 1, 0, 0, 1. Now, for us to find out what a and b are, we can set up two separate equations. If we take a look at the 1 over here, how do we get this 1? Well, I've got the a over here, and I add on to this 1 over b subtract a multiplied by negative 1. And that's how I get this 1. I will call this equation 1. And if I take a look at this 0, how do I get this 0? Well, I would have negative 1 plus 1 over b subtract a multiplied by this 1, and of course that would give us this 0. I will call this equation 2. Now, from equation 2, I can take this negative 1 to the right hand side, leaving me with 1 over b subtract a equaling 1. I will call this equation 3. And what I will do is I will replace the 1 over b subtract a with 1. In other words, we will substitute in 3 into 1. So I have a plus 1 over b subtract a, which I've just said is 1, multiplied by negative 1, and this is equal to 1. So I've got a subtract 1 equals 1, meaning a is equal to 2. If we now use equation 3 to help us find out what the value of b is, we have 1 over b subtract a, so I've got 1 over b subtract 2 because that is the value of a, and this is equal to 1. Rearranging, we end up with b subtract 2 equals 1, so b is equal to 3. A is 2, b is 3. Question 4. For the first part, we've got the matrix P given by 2, 0, 0, 1. Part A, describe fully the single transformation P represented by the matrix P. What we need to do is find out what happens when we apply the matrix P to a general point xy. And so if we do that, we've got the matrix P 2, 0, 0, 1, and we apply this to a general point xy. Let's see what we get. We've got 2 times by x plus 0 times by y, so that's 2x. And then we've got 0 times by x plus 1 multiplied by y, which is y. So P maps the point x, y to the point 2x, y. The y has remained the same, the x has doubled from x to 2x, and so we have a stretch with scale factor 2 parallel to the x-axis. State the equation of one invariant line under the transformation P. Now, an invariant line is a line that maps onto itself. It stays the same. So, since y stays the same, any horizontal line is invariant. For example, we could have y equals 0. This is a horizontal line, and of course y equals 0 is simply the x-axis. For the second part of the question, we've got the matrix Q given by cos 2 theta 0, 1 tan 2 theta, where theta is in between 0 and 360 degrees. The matrix Q represents the transformation Q. Triangle T is transformed to triangle T' by the transformation Q. Given that the coordinates of the vertices of T are 2, 3, 3, 6 and 8, 3, the area of t dash is 4.5, we have to determine the possible values of theta. To begin with, let us find the area of the triangle T. Here we've got the triangle T, and we've got the coordinates of the vertices 2, 3, 3, 6 and 8, 3. We can find the area of T using a half times base times height. So we have a half times by the base. Now we are going from 2 to 8, so the base is 6, and the height we are going from 3 to 6, so the height is 3. A half times 6 times 3, that's equal to 9. So the area of T is equal to. We also know the area of T dash is 4.5. The area of T dash can be found by working out the magnitude of the determinant of Q and then multiplying that by the area of T. This is the area scale factor. The reason we have the magnitude of the determinant of Q is because we don't want any negative values. Now, we know the area of T dash is 4.5, so we have 4.5 equals the magnitude of the determinant of Q multiplied by 9, which is the area of T, which we've just worked out. So we've got the magnitude of the determinant of Q equaling 1/2. So we've got the magnitude of determinant of Q, that's shown here, and this is equal to 1/2. We've got the magnitude of, well, here I've got cos 2 theta multiplied by tan 2 theta, subtract 0 multiplied by 1, and this is equal to 1/2. So I've got the magnitude of cos 2 theta tan 2 theta equaling 1/2. So I've got the magnitude of cos 2 theta multiplied by tan 2 theta, which is the same as sine 2 theta over cos 2 theta, and this is equal to 1/2. Cos 2 theta over cos 2 theta is 1, so we have the magnitude of sine 2 theta equaling 1. So we've got sine 2 theta, which is equal to plus minus 1/2, and we need to solve this between 0 and 360 degrees. Here we've got a 2 theta, here we've got a theta. Let's change the domain. So we've got 0, which is less than or equal to 2 theta, which is less than 720. So we've got sine 2 theta equaling 1/2. Let's solve this. Well, 2 theta will equal the inverse sine of 1/2, which is 30, and the next value will be 180 take away 30, which is 150. To find the next value, we need to do 360 plus 30, which is 390, and then 360 plus 150, which is 510. And dividing these by 2, we end up with theta equaling 15, 75, 195, and 255. We also have sine 2 theta equaling negative 1/2. So for us to find out what 2 theta is, we need to do the inverse sine of negative 1/2, and that's negative 30 degrees. And to find out the next value, we need to do 180 take away the negative 30, which is 210. To find the next value, I need to do the negative 30 plus 360, which is 330. Then to find the next value, I need to do 210 plus 360, which is 570. To find the next value, I need to do 330 plus 360, which is 690. And dividing these by 2, we end up with theta equaling 105, 165, 285, and 345. So we've got the values of theta being 15, 75, 105, 165, 195, 255, 285, and 345. Question number 5. A complex number z is represented by the point P in the complex plane. Given that z satisfies the mod of z subtract 1 equals 1, part A, we have to sketch on an Argand diagram the locus of P as z varies. For part A, we need to recognize we have a circle with a centre of 1, 0 and a radius of 1. So if we sketch that, we have the following. Given that z also satisfies the argument of z plus 1 equaling theta, part B, determine the possible values of theta such that the locus argument of z plus 1 equals theta is a tangent to the locus mod of z subtract 1 equals 1. Here you can see we've got our tangents, and you will notice they are from the point -1. And that's because for these half lines we have the argument of z plus 1 equaling theta, and so the centre would be -1, 0. These tangents will be perpendicular to the radius as we see here. The angle between the real axis and the tangent, I'm going to let theta be that angle. I'd also have the same for this triangle here. I've got a radius of length 1. Here I'm going from -1 to 1, so that has a length of 2. And recognizing this is my hypotenuse, this adjacent length would have a length of √3, and that is quite simply the square root of 2 squared take away 1 squared, which is √3. So, to find out what theta is, we can use simple trigonometry. We've got sine theta, which is equal to the opposite over the hypotenuse, so we've got 1 over 2, meaning theta will equal plus minus pi over 6. And the reason we've got plus minus is because we are below the real axis as well as above the real axis. Part C, hence determine the exact possible complex numbers z. What this question is really saying is we need to find this point here where the circle touches the tangent, and this point here where the circle touches the tangent. And we also need to recognize we will be using the center of -1, 0, which comes from the argument of z plus 1 equaling 0. So I've got z plus 1 equals, now the magnitude, if I go back here, will be √3, and that's going from here to here, multiplied by the cos of pi over 6 plus I sine of pi over 6. And for the one below the real axis, we'd have z plus 1 equals √3 multiplied by cos of negative pi over 6 plus I sine of negative pi over 6. And what we have here then is √3 multiplied by, now cos of negative pi over 6, that's just cos of pi over 6 because it's an even function. And here we've got the sine of negative pi over 6. And if I take that negative outside, I'd have negative I multiplied by the sine of pi over 6, and that's because sine is an odd function. So z will equal root 3 times by the cos of pi over 6 plus minus I sine of pi over 6 take away 1. So let's solve this on our calculator. Let us make sure that we are in radians, and we will display the results as complex numbers. We have root 3 multiplied by the cosine of pi over 6 plus I times by the sine of pi over 6, and then we need to take away 1 from those, so we end up with 1 plus minus root 3 I over 2. Question number 6. Prove by induction that for all positive integers n, the sum of r cubed from r equals 1 to r equals n is equal to a quarter n squared times n plus 1 squared. To do this question, what we need to do is show that this result is true when we replace the n with k plus 1. That is to say, we want to show that the sum of r cubed from r equals 1 to r equals k plus 1 is equal to k plus 1 squared times k plus 1 squared over 4. We have replaced the n with k plus 1. Our first step is to check for n equals 1. On the left hand side of this, we have the sum of r cubed from r equals 1 to 1. And what this is equal to is 1 cubed, which is just 1. On the right hand side, we have 1 squared times by 1 plus 1 squared over 4, which is also equal to 1. Meaning the result is true for n equals 1. We now need to assume that the result is true for n equals k for our second step. In other words, the sum of r cubed from r equals 1 to r equals k will be given by k squared times k plus 1 squared over 4. We have replaced the n with k. For our third step, which is the induction step, we want to prove that the result is true for n equals k plus 1. So I've got the sum of r cubed from r equals 1 to r equals k plus 1, and we need to somehow show, as we have stated here, that it's equal to k plus 1 squared times k plus 1 squared over 4. The way we can do this is to recognize that this is equal to the sum of r cubed from r equals 1 to r equals k plus the next term after this, which is the k plus 1th term, and that's given by k plus 1 cubed. And the rest is just manipulation. We know that the sum of r cubed from r equals 1 to r equals k, that was shown to be k squared times k plus 1 squared over 4. And then we add on to this k plus 1 cubed. What we will do is factorize out the common terms, which is k plus 1 squared over 4. Now you might be thinking this term here doesn't have a quarter, but you will see how factorizing out a quarter can help us show the final result. So I've got k plus 1 squared over 4, and what I need to multiply this by to get this term is k squared. And then I need to add on 4 multiplied by k plus 1, because k plus 1 squared times k plus 1 gives us k plus 1 cubed, and the quarter times by the 4 gives us the 1. So I've got k plus 1 squared over 4, and inside this bracket we would have k squared plus 4k plus 4. So I've got k plus 1 squared over 4, and inside this bracket we can recognise that we've got a perfect square. This is k plus 2 squared. K plus 2 squared expanded out would give us k squared plus 4k plus 4. Now k plus 2, we can rewrite that as k plus 1 plus 1. So I've got k plus 1 squared over 4 multiplied by k plus 1 plus 1 squared. You will recall that's what we have here. And that's exactly what we need to show. So for our fourth step, which is the conclusion step, we state that if it's true for n equals k, then it's true for n equals k plus 1. And as it's also true for n equals 1, that means it's true for all positive integers. Question number 7. Figure 1 shows a sketch of a hot air balloon. When filled with air, the balloon has a height of 24 meters. Figure 2 shows a sketch of the curve C with equation 350x squared equals 12 plus y squared times a subtract y squared, where x is greater than or equal to 0, a is a constant. The balloon is modelled by rotating C through 360 degrees about the y-axis. Given that one y-intercept of C is negative 12, part A, show that A equals 144. For part A of the question, we've got the curve C and we've got the coordinate axis here. The total height is 24 meters, and so this would correspond to the negative 12, and therefore the point here will be 0, 12, meaning the height from the x-axis to the highest point on the curve is given as 12. So this has an x-coordinate of 0, a y-coordinate of 12. For us to find out what A is, we can substitute in x equals 0, y equals 12 into that equation. So we'd have 350 times 0 squared equals 12 plus 12 squared multiplied by a subtract 12 squared. So we have 0 equals, here we've got 24 squared, which is 576, multiplied by this bracket, which is a subtract 144, meaning a is equal to 144. Part B. Use algebraic integration to determine the volume of air needed to fill the balloon according to the model. Give the answer to two significant figures. We need to recognize in this question, for us to find the volume, that will be given by pi times by the integral from our lower limit to our upper limit of x squared with respect to y. So the first thing we need to do is state what x squared is. We know that 350x squared equals 12 plus y squared times a subtract y squared, and we know what a is, that's 144, so we need to rearrange for x squared. So x squared is 12 plus y squared times by 144 subtract y squared over 350. So let's work this out by, first of all, expanding 12 plus y squared. Doing so, that's 144 plus 24y plus y squared, multiplied by 144 subtract y squared, divided by 350. So, if I simplify the numerator, we would have 20,736 plus 3,456y, subtract 24y cubed, subtract y to the 4, all over 350. So the volume will be given by pi multiplied by the integral from minus 12 to 12 of 20,736 plus 3,456y, subtract 24y cubed, subtract y to the 4 over 350 dy. The first thing we can do is take out the 1 over 350 as a common factor. So I've got pi over 350 times by. Now if I integrate the terms here, I would have 20,736y plus 1,728y squared, subtract 6y to the 4, subtract y to the 5 over 5. I need to evaluate this between minus 12 and 12. So I've got pi over 350 multiplied by, now for my upper limit, substituting 12 in, we have the result shown here, and for the lower limit, substituting in negative 12, we have the result shown here. So now let's work this out. So we have 20736 multiplied by 12 plus 1728 times by 12 squared, subtract 6 times by 12 to the 4, take away 12 to the 5 over 5, and then we need to take away from this 20736 times minus 12 plus 1728 times by minus 12 squared minus 6 multiplied by minus 12 to the 4, subtract minus 12 to the power of 5 divided by 5. And then I need to multiply this by pi over 350. So we get 3573.617, etc. Meaning we end up with 3,600 meters cubed to two significant figures. Part C. Modify the equation 350x squared equals 12 plus y squared times 144 take away y squared to model a mathematically similar balloon with a height of 26 meters. So, a height of 26 meters means we go from y equals negative 13 to y equals 13. And so for our equation, we can adapt that by replacing the 12 with 13 and recognizing that a will equal 13 squared. So we have 350 x squared equals 13 plus y squared times 169 take away y squared. Part D. State one limitation of the models. The balloon may not have the same shape as the curve. It might not be as smooth as the curve exactly. Question number 8. The first n triangle numbers are 1, 3, 6, 10, etc. and the nth triangle number will be a half n times n plus 1, where n is a positive integer. Part A. Use the standard results for the sum of r squared from r equals 1 to r equals n, and the sum of r from r equals 1 to r equals n to show that the sum of the first n triangle numbers is a sixth times n plus 1 times n plus 2. So for part A, we've got the sum of the first n triangular numbers, that's given by a half r times r plus 1. We are going from r equals 1 to r equals n. And what this is equal to, well, if I take out the 1/2, I would have the sum of, here I've got r times by r, which is r squared, and then I've got r times by 1, which is just r. So I've got a half times by the sum of r squared from r equals 1 to r equals n, plus the sum of r from r equals 1 to r equals n. So I've got a half of. Now we need to use the standard summation results, and that is shown here in the formula book. For the sum of the r squareds, we have a sixth times by n times n plus 1 times 2n plus 1, and for the sum of the r's, we have a half n times n plus 1. What we can do is as follows. We can take out this 1/2, and then we've also got an n which is common to both terms, and then we've got the n plus 1 which is common to both. And inside the bracket, a half n times n plus 1 times by a sixth times by 2n plus 1 will give me this term, and a half n times n plus 1 plus a half will give me this term here. So I've got a half n times n plus 1, and here I've got this 1/6 times 2n plus 1, and the half I'm going to rewrite as 3/6. So that means what's inside this bracket, we've got this common denominator of 6. So I've got a half n times n plus 1, and here we would have 2n plus 1 plus 3/6. So I've got a half n times n plus 1, and here we have 2n plus 1 plus 3, which is 2n plus 4, and I divide that by 6. So I've got a half n times n plus 1, and 2n plus 4/6 is the same as n plus 2/3. And if I factorise out a 1/3 from this term, a third times by a half, that's a sixth. So I've got a sixth n times n plus 1 times n plus 2, and that is what I wanted to show. Part B. Hence, determine the value of n for which the sum of the first n triangular numbers is 22n. For part B, we need to set this result here, which is the sum of the first n triangular numbers, equal to 22n. Now, the n's cancel on both sides, and if I multiply by 6, we will be left with n plus 1 times n plus 2 equals 132. On the left hand side we have n squared plus 3n plus 2, and on the right hand side we have 132. So I've got n squared plus 3n subtract 130 equals 0, so n plus 13 times n subtract 10 equals 0, meaning n is equal to negative 13 and n is equal to 10. So our only solution would be n equals 10, and that's because n is positive. Question number 9. An engineer detects a source of water below the surface of the ground. The engineer models the situation relative to a fixed origin O. In the model, the surface of the ground is a plane pi with equation x subtract 2y plus 8z equals 1. The source of water is at a point W with coordinates 6, -2, -4, where the units are meters. Part A. Use the model to determine the shortest distance from W to the surface of the ground. The shortest distance will be the perpendicular distance from W to the plane pi, and we can find that using this formula shown here. The perpendicular distance of alpha beta gamma from n1x plus n2y plus n3z plus d equals 0 is shown here. So we've got pi, which is x subtract 2y plus 8z subtract 1 equals 0. I've just rearranged. So therefore d will be given by the mod of 1 multiplied by 6 subtract 2 multiplied by -2 plus 8 multiplied by -4 subtract 1 all over the square root of 1 squared plus -2 squared plus 8 squared. So let's work this out using our calculator. If we go to the catalogue, then the fourth option for numeric calc, then the third option for absolute value, we have 1 multiplied by 6 subtract 2 multiplied by -2 plus 8 multiplied by -4 subtract 1 divided by the square root of 1 squared plus -2 squared plus 8 squared. As a decimal we get 2.7688, etc. So we have 2.77 meters. By considering the model, comment on whether the answer to part A is reliable, giving a reason for your answer. For part B, this may be unreliable, and that's because the ground may not be flat. We've modelled it as a smooth, flat plane. In reality, we'd have rocks and different terrains. To access the water, a hole is drilled in a straight line from a point P on the surface of the ground to W. Given that the length of the hole needs to be as short as possible, part C, determine the coordinates of P according to the model. Here is our plane pi. We've got the point W and we're drilling a hole from W. As we're concerned with the shortest distance, the straight line is perpendicular to pi and passes through W with coordinates 6, -2, -4. And here you can see the symbol for a line which is perpendicular. The normal vector to pi is given by I subtract 2j plus 8k, and therefore we can state the equation of the straight line. that will be given by 6, negative 2, negative 4, plus lambda multiplied by 1, negative 2, 8. And we've shown that here. We know that P is the intersection of R and pi, and that is shown here. So our task in this question is to find out the coordinates of P. So a general point on R will be given by x, y, z, which is equal to 6 plus lambda, negative 2 subtract 2 lambda, negative 4 plus 8 lambda. And so what we can do is substitute this point back into the equation for pi. So we have 1 multiplied by 6 plus lambda, subtract 2 multiplied by negative 2 subtract 2 lambda, plus 8 multiplied by negative 4 plus 8 lambda equals 1. So we have 6 plus lambda plus 4 plus 2 lambda subtract 32 plus 64 lambda equals 1. So we have 69 lambda equals 23, meaning lambda is equal to a third. And what we can now do is find out x, y, and z. So x will equal 6 plus lambda, so we have 6 plus a third, which is 19 over 3. For y, we have negative 2, subtract 2 multiplied by lambda, so we subtract 2 times by a third, that's equal to negative 8 over 3. And for z, we'd have negative 4 plus 8 times by lambda, so we have 8 times by a third, and it turns out we get negative 4 over 3. Meaning, the coordinates of P will be given by 19 over 3, negative 8 over 3, and negative 4 over 3. And that is shown here. Given that the actual length of the hole drilled is 2.52 meters, Part D, use the answer to Part A to evaluate the model, giving a reason for your answer. Well, we found the distance to be 2.77. The actual length of the hole drilled is 2.52. So if I compare these by taking them away, 2.77 take away 2.52, that's 0.25. It's a very small difference. So therefore, we have a reasonably good model. The plane pi1 has equation x plus y subtract z equals 3. The plane pi2 has equation ax plus 3y plus 5z equals 4, where a is an integer. Given that pi1 is perpendicular to pi2, part A, determine the value of a. If we think about the plane pi1, the normal vector will be I plus j subtract k. And if we think about the plane pi2, the normal vector will be given by ai plus 3j plus 5k. These two normal vectors are perpendicular to each other because pi1 and pi2 are perpendicular to each other. So we can use the dot product. We have n1 dot with n2, which is equal to 0. So we have 1 multiplied by a plus 1 multiplied by 3 plus negative 1 multiplied by 5, and this is equal to 0. So I've got a plus 3 subtract 5 equals 0, meaning a is equal to 2, and therefore pi2 will be given by 2x plus 3y plus 5z equals 4. The plane pi3 has equation x plus by plus 13z equals c, where b and c are integers. Given that the three planes form a sheaf, Part B, use algebra to determine the value of b and the value of c. If the three planes form a sheaf, that means they have the same line of intersection. Let's draw a diagram for that. You can see here we've got the plane pi 1, we've got the plane pi 2, and the plane pi 3, and they've got this common line of intersection here. For a sheaf, the normals should be linearly independent. So what we need to do is find the determinant of that. So for our first row, we will have the normal n1, which is 1, 1, negative 1. For the next row, we would have a 3, 5, but we know what a is, that's 2. And then for the plane pi 3, the normal vector will be given by 1, b, 13, and that will be the third row here. And you can see here we are finding the determinant of this matrix. So this is equal to 0. So let's work out what this is, and we can do that by expanding along the first row. We have plus 1, then we cover this row and this column, and we will be left with the determinant of 3, 5b, 13. Then we have minus this 1, and then we cover up this row and this column, so we will be left with the determinant of 2, 5, 1, 13, and then we have plus negative 1. We cover up this row and this column, and we will be left with the determinant of 2, 3, 1b, and this is equal to 0. So I've got 1 multiplied by, now here I've got 3 times by 13, subtract 5 times by b. Then here I've got negative 1, multiplied by 2 times by 13, take away 5 times by 1. And then I've got negative 1 multiplied by 2 times by b, subtract 3 times by 1. And this is all equal to 0. So if we simplify, we would have 21 equals 7b, meaning b is equal to 3. Now, any point on the line where pi 1 and pi 2 meet must also lie on pi 3. And you can see that in this diagram here. Now, let's write down what we know about our equations. We've got pi 1 given by x plus y subtract z equals 3. We'll call this equation 1. We've got pi 2 that's given by 2x plus 3y plus 5z equals 4. Let's call this equation 2. And then we've got pi 3 which is given by x plus 3y plus 13z equals c. We've just worked out the value of b to be 3. Let's call this equation 3. Now, what we need to do in this question is find a line. And because we have a sheaf, essentially we should have the same type of line. And what our goal is then is to look at two of the equations and eliminate x from it. So if I look at pi 1 and pi 2, for me to eliminate the x, I can multiply the first equation by 2, leaving me with 2x plus 2y, subtract 2z equals 6. And if I call this equation 4, we can now do equation 2 take away 4, because that will get rid of the x's. So I've got 2x take away 2x, which is 0x. Then I've got 3y take away 2y, which is just y. Then I've got 5z take away negative 2z, that's 7z, and this is equal to 4 take away 6, which is negative 2. Let's call this equation 5. And now, if I take a look at pi 1 and pi 3, we can do the same thing. if I do 3 take away 1, x take away x is 0x, then I've got 3y take away y, which is 2y, 13z take away negative 1z, that's 14z, then I've got c take away 3. And what we can do is make this equation similar to equation 5 by recognizing on the left hand side we have 2 multiplied by y plus 7z. The right hand side remains as c subtract 3. Let's call this equation 6. What we can now do is substitute in equation 5 into equation 6. We replace the y plus 7z with negative 2. So I've got 2 times negative 2 equals c subtract 3, meaning c is equal to negative 1. Question number 11. F of x equals x cubed, subtract 21x squared plus ax subtract 91, where a is a real constant. The roots of f of x equals 0 are alpha, alpha plus 3 beta, and alpha plus 6 beta, where alpha and beta are real constants. We have to use algebra to determine the value of each of these roots. The first thing we will do is we will let the roots of f of x equals 0 be p, which I'm going to say is alpha, q, which I'm going to say is alpha plus 3 beta, and r, which I'm going to say is alpha plus 6 beta. So the sum of the roots then, p plus q plus r, will equal negative 21. So I've got p plus q plus r, which is equal to 21. I know what p is, that's alpha. I know what q is, that's alpha plus 3 beta. I know what r is, that's alpha plus 6 beta. And adding these together and setting it equal to 21, we've got the equation shown here. So simplifying, I've got 3 alpha plus 9 beta equals 21, and if I divide through by 3, I've got alpha plus 3 beta equals 7, and if I rearrange, I've got alpha equals 7 subtract 3 beta. What we can now do is work out the product of the roots. So I've got PQR equals negative 91. So in other words, PQR is equal to 91. And similar to before, I know what P is, that's alpha. I know what Q is, that's alpha plus 3 beta. And I know what R is, that's alpha plus 6 beta. And I set this equal to 91. So what I'm going to do now is replace the alpha with 7 subtract 3 beta. So I've got alpha, which is 7 minus 3 beta. Then I've got alpha plus 3 beta, and I know that is equal to 7. So I'm going to replace the alpha plus 3 beta with 7, and then I've got alpha plus 6 beta, so that's going to be alpha, which is 7 subtract 3 beta, plus 6 beta, and this is equal to 91. So I've got 7 multiplied by 7 subtract 3 beta multiplied by 7 plus 3 beta equals 91. If I divide through by 7, I've got 7 subtract 3 beta times 7 plus 3 beta equals 13. So I've got 49 subtract 9 beta squared equals 13. 9 beta squared equals 36. Divide through by 9, then square root. You will find beta to equal plus minus 2. Now let's see what happens when we have beta equaling negative 2. What we can do is substitute this back into here where we've got Q and R. And we can also use the equation here where alpha is equal to 7 subtract 3 beta. So when beta equals negative 2, I've got alpha, which is equal to 7, take away 3 times negative 2, which is 13, and alpha plus 3 beta, well, I know what alpha is at 13, so I've got 13 plus 3 times by negative 2, which is 7. And I've got alpha plus 6 beta, alpha's 13, beta is negative 2, so I've got 13 plus 6 times by negative 2, which is 1. And similarly, when beta equals 2, I've got alpha, which is 7, subtract 3 times by 2, which is 1. Alpha plus 3 beta, well, I know what alpha is, that's 1. So I've got 1 plus 3 times by 2, which is 7. And then I've got alpha plus 6 beta, so I know what alpha is, that is 1. And I add on to this 6 beta, so I add on 6 times by 2, which is 13. So I've got 1, I've got 7, and I've got 13. So the roots are 1, 7, and 13.